Hello everyone, and welcome to the AI Research Roundup. I'm your host Alex, where we dive into the latest in artificial intelligence research. Today we're looking at a paper titled Advanced Video Inpainting Using Optical Flow-Guided Efficient Diffusion. This paper tackles the tricky problem of video inpainting, filling in missing or unwanted parts of a video. It proposes a new framework called FloED, which uses optical flow, essentially motion information, to guide the diffusion process. The main idea is to improve both the temporal consistency, making sure the filled-in parts look right across frames, and the efficiency of video inpainting, which can be quite computationally intensive. Okay, so let's look at Figure 1 here. This figure really shows FloED in action, comparing it side by side with another method called contextual. You can see three different examples. The column on the left is the source video with the part to be filled in marked out. Then the middle column shows the result from contextual, and the right column shows the result from FloED, which they label as hours. It covers both background restoration, like filling in parts of the landscape or playground, and object removal, like taking the person out of that last scene. Visually, FloED seems to produce more plausible and cleaner results in these examples, and notice the times listed below. FloED's significantly faster than contextual here, processing the video in about 16 seconds compared to over 26 for contextual, which touches on that efficiency goal we mentioned. Okay, so building on those visual results we just saw, Figure 2 here gives us a peek under the hood at the FloED architecture itself. It's built around this dual branch idea. You have the main Inpainting branch, which uses stable diffusion and a motion module, and then this separate flow branch, you see it in purple, which specifically works on completing the optical flow information from the corrupted input. The training happens in two stages. The legend shows the little flame icons for what's trained when, basically adapting the motion part first, then introducing and training the flow branch and this flow adapter layer. That's the green striped part, which helps integrate the flow guidance into the main process. You can also see how the anchor frame concept fits in at the beginning. And importantly for efficiency, look at the diagram on the right that illustrates the flow attention cache, which cleverly reuses flow information during inference to speed things up, contributing to that faster time we saw in the first figure. Right, so we just saw the overall architecture and the flow attention cache for speeding things up. Figure 3 here zooms in on another key efficiency technique, the flow-guided latent interpolation. Looking at the diagram, you see the denoising process unfolds over multiple steps, t, t-1, t-2, etc. The key thing here is that flow doesn't denoise every frame latent at every step. See those green Z representations? Those are generated using interpolation. The little box on the right shows how it uses the completed optical flow, that motion information from the flow branch, to essentially warp an existing latent representation and predict what an adjacent frame's latent should be. This means it can skip the full denoising calculation for some frames, particularly in the early stages, which contributes to that speedup we saw earlier. Okay, so we just saw how FloED uses things like latent interpolation to be more efficient. Figure 4 here gives us another look at the actual results. Similar to Figure 1, but showing more diverse examples and multiple frames from the output videos. You can see it tackling different challenges, like the flickering fire, the complex motion of water in the forest stream, and larger background areas in the landscape and coastal scenes. It's really showcasing the visual quality and, importantly, the temporal consistency across the generated frames for these varied scenarios. So, following up on those diverse examples we saw in Figure 4, Figure 5 gives us a more direct head-to-head comparison. This time, it pits FloED, again labeled hours, against several other recent methods like contextual, ProPainter, VC, and DC. You can see two main scenarios, one background restoration with the icy water, and one object removal with the person on the stairs. Looking closely, especially across the frames, FloED seems to handle the motion and texture filling much more cleanly than the competing methods shown here, which tend to have more noticeable artifacts or inconsistencies. Okay, now, Figure 8 here takes a slightly different tack from the last comparison. Instead of comparing FloED to other methods, It's actually comparing FloED to itself, specifically, with and without that flow adapter component we talked about in the architecture. This is showing object removal examples, taking out the rows in the prism. You can clearly see the difference. The middle row, labeled with OFA, meaning without the flow adapter, looks quite blurry and lacks detail. But the bottom row, with FA, with the flow adapter, generates much sharper, more plausible results, really showing how crucial that flow guidance integration is for quality. Okay, so we just saw how important that flow adapter is for getting good results in Figure 8. Now, Figure 7 actually shows us the input to that adapter, the completed optical flow itself. You can see the original flow estimated by Raft in the top row, the source video with the mask in the middle, and then importantly, the output flow from FloED's dedicated flow branch in the bottom row. It shows this for both background restoration and object removal, and you can see how the flow branch effectively fills in plausible motion information where the mask was, creating that guidance signal. Right, so seeing that completed flow in Figure 7 really ties it all together. The main thing is how FloED cleverly uses that optical flow information to guide the diffusion process, leading to really impressive and consistent video in-painting results, without being computationally excessive. This kind of approach, integrating motion understanding directly into generation, is super important for advancing AI video editing tools. Well, that wraps up our look at FloED today. Thanks for joining me on the AI Research Roundup. I'm your host, Alex.